G'day, in the last part we derived something pretty cool, I think. What we derived was that for a function y of x that can be differentiated n times at the point A, we found that actually y of x minus something that we called on of x must be equal to y at the point A, y of A, plus y differentiated at A times x minus A to the power of 1, plus y differentiated twice at the point A times x minus a squared divided by 2 factorial plus, and we keep doing this, we can do this up to n times, so plus y differentiated n times at the point A times x minus a to the power of n divided by n factorial. And the reason why we need it to be differentiated n plus 1 times at the point A is this on of x term here. On of x is a little bit nasty. On of x is actually equal to the integral from a to x of the integral from a to t1 all the way to the integral from a to tn of y differentiated n plus 1 times, and we use a dummy variable tn plus 1, and then we take the integral with respect to t1 all the way back to t2, dt2, and then dt1 is the last dummy variable we need. So actually all of these guys here is t1 all the way up to tn, so t1, t2, t3, all the way up to tn. These are all dummy variables. So the interval from a to x, that's the interval we're really concerned with. A and x are the real things that we're using. T1 to tn, we're just using those for the purposes of integrating this thing. So that's kind of important. Oops, dropped my pen. Okay, something else to notice. Well, let's take a look at on of x for a second here. Well, on the one side, we've got y of x minus on of x is equal to, and on the other side, we've got this huge thing here. What happens if we just keep letting n get bigger and bigger? So we say n tends to infinity. This means n gets bigger and bigger and bigger. What happens? Well, actually, I guess whatever happens depends on this on of x, since the two sides of the equal sign are equal, but on this side we only have on of x, so it only depends on n in this on part. So when n gets bigger and bigger, if on of x gets closer and closer to something, then the other side's going to get closer and closer to something the more terms we add on. So let me say that again. If this side, if the on of x in particular gets closer and closer to something as n gets bigger and bigger, then this side is also going to get closer and closer to something the more terms we add on. So let's suppose it does. As n tends to infinity, suppose on of x tends towards L. So as n tends to infinity, suppose on of x tends towards L. Well then, in that case, let me go to a new board. In that case, we must have that, well, the limit as n gets bigger and bigger of y of x minus on of x must be equal to the limit as n tends to infinity of this thing on the other side, which I'm going to write now as the sum from k equals 0 to n of y differentiated k times divided, at the point A, divided by k factorial times x minus a to the power of k. X minus a to the power of k. Well, the limit on this side, well, as n tends to infinity, we said that on of x got closer and closer to L, so this whole thing must get closer and closer to y of x minus L. And on the other side, as n gets bigger and bigger, Well, basically we're just adding more and more terms on, and we write it like this. We write it as the sum from k equals 0 to infinity of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. And of course, what this sum thing here means, it just means you put in k equals 0. So you put in k equals 0 and you get y differentiated 0 times. So that's just y at the point A divided by 0 factorial, or 0 factorial is 1, and then times x minus a to the power of 0, or anything to the power of 0 is 1, so we just get y of a. And then you put in k equals 1, and you get y differentiated 1 time at the point A, divided by 1 factorial, again 1 factorial is still 1, and then times x minus a to the power of 1. So just times x minus a. And again, you put in k equals 2, and you get y differentiated twice at the point A, divided by 2 factorial times x minus a squared, and so on. And because we're going to infinity this time, basically you just keep doing it forever. In fact, we don't actually keep doing it forever. What we do is we do like a whole bunch of them, and then we realize, okay, these things are getting closer and closer to some number, and whatever number they're getting closer and closer towards, that's what this guy here is. And that's what the other side is as well, because they're equal to each other. Okay, so that's that. And this big complicated sum thing, oops, this thing here, put a green cloud around it. This thing in the green cloud, that is called the Taylor series. Ta-da! So that is the thing we've been deriving this whole time. And notice that it only works, we only get a Taylor series if these ONs get closer and closer to some number L, as n gets bigger and bigger. If they don't get closer and closer to some number L, then this side will not converge. This side is not, oh sorry, not this side, this side up here will not converge because it's not getting closer and closer to anything, and therefore this side here also won't get closer and closer to anything. So we need these ONs to get closer and closer to some number. Okay, so let me write it out again one more time, just to really make the point in case it wasn't made already. If limits as n tends to infinity of ON of x is equal to L, then the function has a Taylor series, and the Taylor series is equal to yn of x minus L, which is the series k equals 0 to infinity. Oops, I put an n where there shouldn't be an n in the y part. Y of x, rather, not yn of x. We haven't even defined yn of x. Yn of x is meaningless at the moment. So y of x minus L is equal to the Taylor series, which is the sum from k equals 0 to infinity of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. And for this to work, obviously, we need On of x to have a limit as n gets bigger and bigger. And for On of x to even make sense, we need y is infinitely differentiable or not only at the point x equals a, but on a to, I guess, x. Yeah, and it doesn't have to be differentiable at x, I don't think. So it has to be differentiable on the integral, on the interval between a and x, and I guess not necessarily at x, but definitely on the interval between a and x. Okay, anyway, that's the Taylor series right there. And just a heads up of what's coming next. What about this L? So if this L is equal to 0, in other words, if these ON of x gets closer and closer to 0 as n gets bigger and bigger, then we can actually write y of x in a special form. We can write y of x as its Taylor series. So if ON of x gets closer and closer to 0 as n tends to infinity, then y of x is equal to the sum from k equals 0 to infinity of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. Now this only works if L equals 0, if ON gets closer and closer to 0 as n tends to infinity. Okay, and we're going to take a look at what are some ways we can see that happens in the next video. Thanks very much for watching. Don't forget to check out the notes and have a go at the exercises at the back. Thanks very much. See you in the next video. Take care. Bye.